Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 35. Now we are entering into a stage where we will be leaving the bulk MOSFET single gate and we will be exploring into the domain of emerging FET technologies, right, or technologies which have developed primarily post 2000 in the domain of FET. So, the first therefore topic is basically the double gate MOSFET. So, I will try to introduce to you double gate MOSFET in this week. Then we will look into SOI MOSFET, which is partially and fully depleted MOSFET. Then we will look into the subthreshold swing and transconductance, and then finally look into the small and large signal model, and then I will give you a brief insight about the junctionless MOSFET, relatively a new MOSFET which has come out replacing the conventional MOSFET. Let us first of all understand what is a double gate MOSFET, how it structurally looks like. Then we will be breaking them down into various fabrication steps through which these double gate MOSFETs are fabricated. We will look into the energy band diagram, electric field profile, and then inversion, electron density profile. So, basically we will look into all these factors as far as double gate MOSFETs are concerned. Now, the prerequisite knowledge here is that I would recommend you please study the basic fabrication steps of CMOS procedures, right, where you know how a epitaxial growth is there, what is the meaning of CVD or chemical vapor deposition, and basic fabrication steps of CMOS. That possibly I will not be able to give you an idea, but at least I will be able to give you the fabrication steps of a double gate MOSFET and tell you the energy band diagram. Till now, if you look closely to our way the lecture was proceeding, we were all assuming that the device is basically a 4-terminal device, and therefore there was a gate terminal, there was a drain terminal, there was a gate and source terminal, and there was a body terminal, right. What was the body terminal which we were referring to? The body terminal was primarily the substrate terminal, right, and the body terminal was giving me control of the threshold voltage of the device. I was able to control the threshold voltage of the device by using the body, right, and we had looked into it in detailed manner in our previous lecture. However, sort of not a rule of thumb, but an very common sense approach to the whole problem is that if you are able to control the channel by the gate in much better manner, then all your second order short channel effects will reduce. The basic idea here is that if you are able to control the channel by gate is more then SCE or the short channel effects are reduced, and that was the logic behind which double gate came into picture. That now rather than having only one inversion layer, if you can replicate the same gate right on the back side, as you can see on the right hand side of the figure, this one, then we define this to be as a double gate MOSFET. Why double gate? Because there are two gates, one is this gate, right, and the other gate is this one. And this is source drain still remains the same of having large doping concentration here, N plus and N plus here. So, it is a large doping concentration which you see, and you have the silicon layer here. This is the silicon thickness layer, which is basically the body layer, and this is the distance between the two gates. So, the distance between the two gates is basically T silicon plus 2 Tox, where Tox is the oxide thickness at this particular point and at this particular point. I am assuming at this stage that these two oxide thicknesses are almost the same. The drain and the source have exactly the same doping concentration. So, there are no second order effects coming into picture, everything is fine, and I have a metal contact here. Through which I am able to have this gate voltage being applied. I can also have these gate voltage sort of tied to each other. So, let me show to you. I can tie these two gate voltages. I can do like this and give a single power supply to this as well as this, maybe a positive power supply or negative power supply. Then we define this to be as a tied gate configuration. This is known as the tied gate configuration. And if you want to have an independent sort of operation, then you give a bias here, right, and you give a bias here, and these bias may be independent. So, V1, V2 and so on and so forth. This is known as a independent gate configuration or position, right. So, you can use both of them, but in most of the cases we use the tied gate configuration. Since this is a double gate MOSFET, as you can see, your on current will therefore double, almost double itself, and that is what is written here, that the on current increases, right. And the increase in the on current is primarily because of two channels being available. One channel is here, another channel is at this particular point. Therefore, if you look very carefully, this device, which is a double gate device, DG device, has got superior characteristics as compared to a single gate device, because the electrostatic control of the gate is much better, and therefore, dibble, jiddle are much lower in this case as compared to a single gate MOSFET, right. And that gives you a brief idea about why a double gate MOSFET is preferred over a single gate, obviously with few changes in the fabrication procedure. So, that is what is written here. The short channel effect reduction takes place, and there is also a reduction of the leakage current. I-on increases, right, but your I-off also reduces down, and therefore, I-on to I-off ratio, which is quite a critical sort of parameter, is much better in case of a double gate MOSFET as compared to a single gate MOSFET. Okay. If we go ahead and check out each one of them, the advantage therefore is reduced short channel effect, reduced leakage, low off state power which you get. The below figure which you see here is a figure of a FinFET actually, but I have a hard mask which is an oxide layer here. This is an oxide layer, this is silicon, right, and this is your metal gate which you have put, and it is surrounding in all the three sides. But what I have done is, interestingly, that this oxide layer at the top gate is much. So, if I define this as TOX1 and this as TOX2, then TOX1 is much larger as compared to TOX2, primarily meaning that the top layer gate is further away from the fin, and therefore, this effectively behaves like a double gate MOSFET. So, I hope structurally this can be, FinFET can be converted to a double gate, provided you have, this is structure of FinFET we will study later on, but this structure is very simple. This is a gate, I have a source on this side and I have a drain on the back side of this, of your screen. So, the current flows in this manner inside the screen, right, and from drain to source the current will flow, the conventional current will flow, and who will create the channel? The gate will create the channel. The red colored material which is placed here will create the channel. So, this channel length is defined as the length from this point to this point. We define x to be in this direction and y to be in this direction. So, x 0 point is this one, 0 point is the intersection of the source and gate, and I am also assuming that the gate source and the gate drain overlap is 0, which means that there are no parasitic capacitances because of the overlap. That assumption has been taken in this study. So, let us come to a double gate fabrication process. What you see to the right here, right, is basically the image of a double gate MOSFET, where this is the metal gate which you see. I have a source drain. So, if we will go step by step and explain to you the whole fabrication procedure here at this stage. So, let me add to what the device or the structure tells me here is that if you look very carefully in this case, this is my source, right. If you take this, right, and if you take this is the drain, and with cavity will actually let you allow the growth of the metal layer here, and this is the source. So, I have the source here, this is the source, this is the drain, this is my gate, this is basically the gate, this red colored is my gate, right. So, this is an optical microphotograph of a device with two gate fingers. Why two gate fingers? Because there are two gates here. So, there are two gate fingers. So, this is basically a micrograph, right, rheitograph with two gate fingers, one is gate number 1 here, gate number 2 here, and what we are doing here is that the width divided by L, W by L is approximately equals to 3, and we have taken the channel length to be equals to 2 micron. So, effectively the width is actually equal to 6 micron. In a sense, an example of using a single structure using two fins, 2 fingers, I will be able to generate 2 DG-MOSFETs at this particular point, and the gate is available here. Now, the idea here is that we can actually make the W by L ratio change drastically at the fabrication stage in order to check the current flow in the device. If you look at these are basically cavities which are actually being created in order to reduce the vortex problems when you grow a CVD. When you do a CVD, there is a problem known as a vortex effect, right. In order to reduce the vortex effect, which basically means that how the chemical vapor is deposited because of vortex is not a good idea, and therefore we try to create these cavities which will reduce the vortex effect of vortex on this thing. Now, when the material is actually in a vapor phase, right. So, when the material is in the vapor phase, what happens is that that the vortex flow will actually, the solidification of gases will be faster. The solidification of gases will be much faster than the flow rate, which means that the flow is coming slowly, but the solidification is happening faster, right, and that will induce errors and will induce some defects within the system. So, that is the reason a cavity is introduced in order to compensate for that change in the vortex flow. Now, let us take one by one step and quickly finish off the double gate fabrication process, and let us see how it works out. So, the proposal here is, if you look, it is from A, B, C, D, E, F, G, H and I. So, there are 9 steps effectively which is being shown here, and each step has got a specific meaning for that. And this is primarily based on the fact that high quality film will be transferred, right. The thin silicon layer will be transferred from the SOI wafer. SOI is silicon on insulator wafer into a thermally oxidized bulk silicon material, and you will have dry etched oxide cavities there through which you will be doing it. So, let us go one by one quickly across the double gate fabrication process. Now, the fabrication process primarily is divided into 2 parts. The first part is basically the pre-processing, and the second part is the CMOS process flow. So, pre-processing implies that you need to first thermally oxidize the material and so on and so forth. Following this, you create bottom gate cavities. So, you see, you first of all part A of the double gate metallization gate fabrication process is, you basically oxidize the silicon wafer, then you do an RIE plasma, basically you do an RIE plasma, and then you do a wafer bonding, right. And the bottom cavities basically means this is the cavity here. The bottom gate cavity are patterned with SF6. SF6 is sulfur hexafluoride, which is based RIE plasma, and as a result you will start having these etches. You see this etchant is there. Since you have etched a cavity here actually the double gate back gate will be actually fabricated, and you do a wafer bonding here. So, when you do a wafer bonding like this, a cavity is created in this manner. So, this is my SOI device, silicon, the SOI means silicon on insulator. So, I have a SOI device, and this SOI device is there, and after this you have a thermal oxide. This is my thermal oxide, thermally grown oxide layer, fast grown oxide layer, and I have this RIE etched cavity, and the back gate is basically my silicon substrate here. Now, therefore, a standard SOI wafer is bonded to the pattern of thermal oxide bulk handle wafer. So, you see here, this is what the first basic happens. You do an external grinding. When you do the grinding, the upper layer gets grounded. So, this is what you do in the first place. Both the exposed surfaces of the wafer, pair of the wafer are bonded together and are treated with warm HNO3. with warm HNO3. Nitric acid is used because it enhances the formation of silicon hydroxyl group. Silicon, this group is enunciated, and which in turn leads to formation of hydrogen bonds, which are much stronger than the normal van der Waals forces, right. And therefore, plasma activation, physical plasma activation using oxygen is generally avoided in this case. So, let us look at this figure. So, what you do is that you do an LPCVD nitride for protection, you grow a nitride layer at the side wall, so that the oxide layer and the semiconductor silicon layer does not get buffered or battered with external voltage, and therefore, you put an LPCD here and then you do a TMH etching here, right. So, you do a nitride deposition followed by an etching. Once you do that, you end up having this the upper layer is etched, and what you are left is basically the thermal oxide, the silicon substrate, and a RIE etched cavity is left. This is basically your D part is done here. Now, so basically you do an annealing in this case, right? You do an annealing in this case. Now, if you do an annealing, then what happens is that this will further strengthen the bond. So, once you do an etching, a further strengthening of the bonds takes place, right. So, this is strengthening of the bond. Now, the grinding process, the way you grind it so that it becomes a very good surface at the top, you do it in 10% TMAH, which is basically tetramethyl ammonium hydroxide. You do an etching using this solution, and after removal of the silicon material, the buried oxide of the soy wafer is removed with buffered hydrofluoric acid, BHF. So, that is what is written here. So, after you have removed the remaining of the silicon material, the box of the soy, box is basically buried oxide. Buried oxide is basically thermally grown large thickness oxide which is there, that can be removed using a buffered HF6 or hydrofluoric acid solution easily, and the rate of etching will be quite important in order to etch out the box layer, the buried oxide layer, right. And this gives you therefore typically the silicon nitride which you have grown, silicon nitride is approximately 0.2 micron thick, 2 micrometer thick silicon which you grow. Now, let us do a reactive ion etching, RIE, right, in order to etch the surface and then pattern a metal layer over that in order to form the double gate MOSFET. Now, the patterning of the active silicon island by RIE is done, and the silicon active islands are defined using RIE. Where I am defining it, you just have a look here. If you look here, this is where you are doing your active zone RIE etching here, right. Once you do an etching, you can actually for the subsequent growth here, you are actually putting a layer here, etchant layer here. So, what will happen is that once you are able to etch the downward one, you are left the resulting structure is therefore a very thin suspended silicon layer above the cavity. So, you have this cavity here, this is the cavity, and above which you have this thin silicon layer is here, and this will be corresponding to the back gate while we do the next set of this thing. Now, this RIE, right, this is followed by a simultaneous thermal oxidation of the top and bottom gate and filling of the polysilicon by CVD, right. So, you need to fill up the polysilicon, and from there you do a top gate and bottom gate etching. Next, the polysilicon is doped using the flow of a dopant gas, right. When you flow the dopant gas, which is you can see here, you are flowing the dopant gas, and then the dopant gas when it flows tries to react with the silicon and forms the dopant species there. Now, we have to be very cautious that the top gate and the bottom gate should be perfectly aligned, right, and this alignment is done by photolithographic steps. There are other techniques of alignment. If there is no alignment, there will be parasitic capacitances later on coming up, right, and that is the reason that is quite critical for understanding the this structure in that sense. Now, let me come to the polysilicon gate here. Once you grow the polysilicon gate, this is the polysilicon gate, this is the polysilicon gate which you are doing, and then what you do is, then you do a patterning here. This is the patterning, and this comes out to be source, drain, and this is the gate here, right, and these are the these are the gate here which you see here. This is the gate, this is the gate, right, and this is the source drain. So, and this is the final value of what I was trying to discuss with you, which I showed to you in the first slide. So, this is a basic idea about this thing, and this whole thing is taken from this paper, Raskin paper, and this was developed way back in 2007, right. So, more mature technologies have come up in the fabrication of these double gate devices and MOSFETs. So, now let us come to the energy band diagram of a double gate MOSFET. Now, if you can look here carefully, the bulk silicon, if you see, this is the N plus gate which is there. If I apply a potential there, the drain layer will be actually like this, and the source layer will be also actually like this. Because of lateral diffusion, there will be some extension of the N plus region inside the gate region. Now, when you apply a bias on the substrate side, then you tend to make your EC and EV go down. If you look at that point, let us compare to the right hand side double gate diagram here. So, you will apply a positive bias, let us apply no bias under this condition. So, these are straight lines which you see here, but however inside the body, if the biases are there, then there will be small disturbance within the body itself, how the energy band diagrams looks like, right. This is the lateral direction which I am talking about. So, this is my N plus gate here, I have an N plus gate here and a body here. So, this is the energy band diagram of double gate MOSFET. If you look at the electric field in this case, you see the electric field flux is centered very large towards this edge, and if you took a double gate, then obviously this edge and this edge, right. So, the drain gate edge is the place where you will have the largest flux of electric field, right. There will be largest flux of electric field in this case, right. Now, why there will be largest flux in the electric field? Because this is the point where the voltages are maximum electric fields. Therefore, not only maximum, the surface potential changes drastically at these two places. Which two places? The first is this one and the second is this one. So, once this happens, the electric field flux becomes very high, right, and that's what you see here. You see they are very dense at this particular point and at this particular point, and as you can see here, there is a finite overlap between the gate and the drain, both for the top and bottom. We have taken approximately 20 nanometer as the as the silicon thickness, and you can appreciate that the electric field will be relatively much higher in this case as compared to that in the single gate devices. Now, let us look at the right hand side electron density profile. So, this is my double gate MOSFET. I have applied a positive bias on the gate, front gate and bottom gate, because of which what has happened is there is a large amount of charge carriers concentration near the silicon dioxide of the interface at the top and at the bottom, right. So, this is basically a spacer, we do not worry about it, just an oxide layer which I have put here, or any HFO2 or even silicon dioxide you can put. These are known as spacers. These spacers tends to reduce the short channel effect and make the device more controlled device. So, gate now has a better control over the device as compared to that of the source and drain. Now, these spacers which you have put here incidentally tend to make the electric field or the electron density go very low at the middle of the channel, and it becomes very high at the edge of the channel, right. This is basically an inverted MOS device which you see here. I am not discussing here, but you will see that for a very large gate voltage, and when the dimension of this T silicon is very small, maybe less than even 5 nanometer or 4 nanometer, you will actually see volume inversion, which primarily means that rather than electron density being maximum at these two edges, it is maximum at the center, right. They try to push the electron at the center, right, and you will have large suddenly increase in the current, because at the center the electrons do not face any silicon dioxide interface, and therefore if you apply a potential, it will move very fast across the interface, provided your channel thickness is very small. Why? Because the electric field of the first order will be applied gate voltage divided by T silicon, gate voltage by T silicon. So, when your T silicon is very small, your gate voltage, even if it is relatively small, the value will be very large, electric field value, which is this value, will be relatively very large. When this is very large, you tend to have this volume inversion can happen, and the whole volume will be inverted, but the edges will remain the same, right, and the current suddenly increases drastically in that case. So, this is symmetrical DG MOSFET. So, they can be asymmetrical DG also. Asymmetricity comes from the fact that if the top gate material and the bottom gate material is not the same, or if the top layer T oxide is not same as the bottom layer T oxide, then also it is asymmetrical in nature. In most of the cases, we try to keep the double gate MOSFET symmetrical in nature, and the reason being that in symmetricity we therefore know, we can predict a priori what will be the value of the current flowing because of the on current at these two edges of the gate. With this, let us recapitulate what we did, and let us finish off this topic. That what we learned is basically learned at least a basic idea about double gate MOSFET. You can actually learn many things, it is available on the net in many of the books, but double gate MOSFET basic idea I have given you, and how is it advantageous with respect to a single gate MOSFET. We have also looked into the process steps, which basically means we are looking into the fabrication of double gate MOSFET, DG MOSFET, we say with DG MOSFET. All the steps which we got. More recently, you can look at many other papers to understand the discussion, and we went then for energy band diagram, energy band diagram of double gate MOSFET, right, and from there we looked into the energy density plot of a TCAD based double gate MOSFET. This gives me a brief idea about the advantage and application of double gate MOSFET to designing any digital circuits or even analog circuits. So, with this I stop this lecture, and thank you for your patient hearing.